That is cool because the die size also relates to the speed of the transistor, like how fast they can transition, and also power consumption because the smaller the surface area, the less energy it takes to switch the state of a transistor. So this is it's kind of cool. It's kind of interesting. Yep.
Yeah, so since we're probably going to be going all online sometime soon, I think.
We do not know. That's the whole thing is administration of the Los Rios district has told us to be prepared to go 100% online.
Okay.
Um, but whether we are actually going to go 100% online depends on the situation, and no one can actually tell what the situation is going to be. Nobody that I know of has a crystal ball, that can say, okay, we're gonna go or whatnot. We are not gonna go. I think with this class, it's not too bad, to go 100% online, because all that means is I don't have to drive here to record myself, and I can be home doing the same thing at the same time, using the same YouTube channel. Okay, um, and that won't be too much impact as far as we're concerned. But for some of the other classes, there will be like major impacts, like nursing classes. Okay, huh?
Weight training.
Weight training.
The great dependent on me being there.
But
Yeah.
you can always lift something at home, right? I mean, you got chairs, tables, you got refrigerators at home, right? I mean, just lift that, right? Yep.
There's like a business that's like cutting around here. There's a business that's cutting their employment because supposedly three instructors here got infected and they weren't even full time.
Oh,
But I guess like a business is like they're cutting people's hours and they're not gonna allow people to work for a couple of days.
yeah. So the whole thing is still really very much in flux. But as far as 440 is concerned, if they let me teach online, distribute instructional lecture online, it's not a big deal. Okay. If we do go online, I have other ways for you guys to interact with me in real time as well. So it's just like taking the class here, except you won't be talking or raising your hand. You'll be chatting on the side, when you're watching the stream. Yes, go ahead.
For those of us worried about Corona, would you be willing to forego the idea of keeping track of absences to drop us during this time?
Well, I have not been taking attendance for a while,
Yeah, understandable.
so I have no evidence to drop people for the time being.
Yeah.
Yeah. So I think I'm gonna relax that a little bit, but that means people will still have to catch up with the content on their own, okay? Because just because they're not here and I did not take roll doesn't mean that, it's an excuse of, well, can you make the test easier, right? I mean, that's not gonna happen, even if I wanted to, because I don't know how to make easy tests. All right. So that whole thing, is kind of volatile. I'm not gonna spend too much time to speculate, what's gonna happen. Yep, go ahead.
Will you be using Zoom or you use YouTube?
So I did some investigation today, and I found that Zoom has no DVR capability. At least the accounts that the district can help me set up with. So that one has no recording capability. It streams just fine. Okay, it has some other additional features. So you guys can all kind of join the same room with your video and whatnot. And I think most people are not going to do the video, the other way around. Um, so it doesn't really buy me anything. But I'm just going to stick with YouTube. You guys know where to go, and it seems to be reasonable in terms of quality. And the best part of YouTube is it is recording. The DVR thing is just there. It also has automatic captioning, like after a while. It also has a chat feature on the side. So if I do go live and make it public, you guys can just watch the live stream, and then you can chat on the side, and then I can answer questions, in real time.
It'll be at the same time, I'm assuming.
Hmm?
It'll be at the same time, I'm assuming.
Approximately the same time. There's about a 10-second delay.
Oh, I mean, like, well, it'll be starting like the same time. Like,
Yeah, yeah. So I'm going to keep the same time slot, except you guys will all be home or somewhere else. Hopefully, not driving Lyft or Uber at the same time. Okay, while you're attending the quote unquote lecture, right? I mean, so I'm ready to go 100% online, but I cannot assume the same thing for all other classes and all other professors. Okay, so that's the one part that That is kind of tricky. Yep. Oh.
Would it be okay as if right now we start watching your online feeds?
Nope, because right now we are still, the district has not said that we are going to go fully 100% online yet. So this class technically is still a face-to-face class. So even though I'm not taking roll, you're still expected to be here. Okay? All right, so with all of that said, okay, the first thing we're going to do is to talk about the homework that was due today. Okay, because I did tell you guys that last week, I would release the homework, and I did release the homework. And I think you guys got an email, right, when I release a homework? Yeah. Yeah, okay. So we'll go over that, and then we're going to get a new homework or new homework today. So we'll go ahead and take a look at this one. It's due today. Okay. All right. Okay. So question number one is asking, consider the not equal to relation over all integers. Okay, so what does that mean? Well, do we know not equal to mean? Okay, it's the same not equal to that you learn in C and C++, okay? And we're defining it over integers. So we know what integers are. Can we compare two integers and know whether the two integers are not equal or not? Okay, so that's all we need. So what we want to answer this question and check all the things that apply in this case. Okay, so we'll start with things that are more obvious. Is it reflexive? Is a value not equal to itself? Obviously not, right? A value always equals to itself, so not equal to is definitely not reflexive. Is it symmetric? If A does not equal to B, does B not equal to A? Okay, so it is reflexive, or it's a symmetric. Next question, is it anti-symmetric? So do you guys remember what is anti-symmetric? So if you see something like this in a test, okay, and you say, I know what is symmetric and anti-symmetric, I'm not quite sure. Tech did say that anti-symmetric is not the same thing as not symmetric. So what do? You look up the definitions, okay? So the definition of anti-symmetric says, okay, pick two things out of the set that the relation is defined over. In other words, in this case, pick any two integers, okay? We'll call those E and F, okay? And it says E relates to F and F relates to E implies that E and F are the same. That's anti-symmetric, okay? If you pick any two integers and you can still claim that is true, then not equal to is said to be anti-symmetric as a relation. So the question is that true? If I pick any two integers E and F, E does not equal to F and F does not equal to E implies that E equals to F. Nope.
Different values? No, if you pick the same value, yeah, so it would be no.
But the qualification is this is a universal qualifier, which means we have to say this is true no matter how you choose two integers.
Yeah.
So the answer is
No.
no. Okay, so we do not check anti-symmetric as a box. Question?
No.
Nope. Okay. All right. So there's one more which is transitive. Okay. Now in transitive you have to pick three values. Okay. So we'll pick E, F, and G in this case. Transitive says if E does not equal to F and F does not equal to G, then E does not equal to G. Is that true or not? For all different ways of picking those three values. No, because you can pick E and G to be the same thing and F is different. Like 1, 3, 1. 1 does not equal to 3 and 3 does not equal to 1, but it does not mean that 1 does not equal to 1. Okay? So it is not transitive either. So now that we have worked out the more basic ones, the next question is it partially ordering? No, because in order to be partially ordering, it needs to be reflexive, antisymmetric, and also transitive. And it's missing all of those items. And is it totally ordering? If it's not partial, it probably is not total, right? So the answer to this question is just symmetric. Question number 2, kind of the same deal, except this one is equal to. So first question, is equal to reflexive? If I pick any value, does it equal to itself? Okay, so it is reflexive, very good. Second question, is it, let's pick antisymmetric next, okay? Is it antisymmetric? If I choose any two values, okay, and they can be the same, if A equals B and B equals A, does it mean that A equals to B? Yes, okay? So it is antisymmetric. Let's look at transitive. Is it transitive? If A equals to B and B equals to C, does it mean that A equals to C? It is also transitive. Okay, that's kind of cool. Is it symmetric? If A equals B, does it mean automatically that B equals A? If A does not equal to B, does it mean that B does not equal to A? Right, so it is symmetric. So now the question is it partially ordering? Yep, it met all the basic requirements of partially ordered, but is it totally ordered? If I pick any two values, any two integers, does one always equal to the other one? And no. Okay, so it's not totally ordering. It is only partially ordering. Is that okay? Do we have any questions of why it is not totally ordered? No questions? All right, we'll move on. Question number 3. If R and S are both relations defined over X, X is a set, so are R and S, but they are basically a set of tuples instead of elements of X. And we also know that R intersecting with S is reflexive. Then what do we know for sure about R itself? Okay, so when you look at the intersection has all the two tuples that are common to R and S, and that is already reflexive. So what does it tell you about R? It has to be reflexive. So this one is easier because it's not like check all the boxes that apply. Only one box applies. Do we have any questions of why the other ones are not necessarily true? Okay, so we are good with this one.
Could you actually explain how that's the case? I have trouble understanding how to make sense of this question, actually.
Okay, so let's check out how to read the question itself. So it says, okay, let me zoom in because I think this time we have to take a closer look. So it says if R and S are both relations defined over X. Do we understand what that means? So R is a subset of X Cartesian product with X, so is S. Okay, so they're both subsets of the Cartesian product of X and X. And we also know that R intersecting with S is reflexive. Do we understand what that means?
It means that the values that are inside X as well.
So that means if you look at the intersection between R and S, okay, for every element in X, it relates to itself, not even as R or S, just looking at the intersection, it is already reflexive. Is that okay?
Quite understand. So it's reflexive.
So the question now is, yeah, go ahead.
So, I also had trouble with this question, but, the thing that kind of clicked,
Uh-huh.
the R intersection with S is
It's smaller.
yeah,
It's potentially smaller than both R and S.
yes, but,
Right.
It's the elements that are in both R and S
Mm-hmm.
Anything extra is just extra. It automatically
That
makes
is correct.
either reflexive.
Yep. So is that entering the question? Yep, go ahead.
Is it not possible that in this situation, S is what's reflective and R is not reflective?
You are correct. R and S are both guaranteed to be reflexive because the common part between the two is already reflexive. So R can have some extra stuff that makes it maybe transitive and other things, and R and S may have some other stuff that makes it anti-symmetric or whatever. But we know that they both have to be reflexive because we know the intersection is reflexive already. So this kind of question is intentionally trying to make you combine what you learned about set operations and combine that with what you now learned about relations. Because they're all related, okay? They're all related, no pun intended. Because all of these are relation questions. Question number 4. Consider the less than relation over integers. So I'm hoping we all understand what is less than in this case, whether one integer is less than another integer. Which of the following relation properties apply in this case? So once again, we'll start with reflexive, okay? Is less than reflexive? No, it is not reflexive because by definition, if A is less than B, A does not equal to B. Okay, so it's not reflexive. Next, is it symmetric? If A is less than B, does it mean that B is less than A? No. Definitely not symmetric. Okay. Is it anti-symmetric? If A is less than B and B is less than A, does that imply A equals to B? Now, this one is super tricky. Yep, it is true. Okay? But then we go like, but that never happens. You can never find two integers where A is less than B and B is less than A. That doesn't happen. But that's exactly why it is cool and we can just come up with a conclusion, because if the left-hand side of an implication is guaranteed false, then the implication itself is guaranteed true. No matter what integer you pick, it's going to be true.
Okay,
Okay?
so that logic, could that one other operator, I forget what it was already, that we used anti-symmetric on, would that also be filled in?
What? Which one?
All right, so can you scroll up real quick? I don't really remember exactly which operator it was. I think it might have been equal to or greater than or equal to or something. Something we said was
No, we haven't seen greater than or equal to. It's not equal to versus equal to.
Okay, so it would be the first one.
The first one?
Yeah.
What about it?
Not equal to. So why would it not be anti-symmetric then, if considering the logic of the
Okay, so
application?
so let me write it out. Okay, I'm hoping you guys, when you tried to answer these questions, you had your notes in front of you, or have my notes in front of you, because that's kind of how what you need to answer the question. Okay, so what is anti-symmetric? Anti-symmetric says for all. Okay, so I'm just going to spell it out using English here. For all EF in whatever the set is, in this case integers. Okay, so we'll make it integers like Z. Okay, the following has to be true. Okay, what are we talking about? We are saying if E does not equal to F and F does not equal to E, this implies that F equals to E. I'm just using extra parentheses to make sure that we understand which part is which part. Okay.
Oh, okay.
So now we can quite clearly see that that's not going to happen,
Right, yeah.
right? Because if you pick E to be 1 and F to be 3, 1 does not equal to 3, it's true. 3 does not equal to 1, it's true. But 3 equals to 1 is false.
Okay.
So now you have, true implies false, which makes the implication itself false.
All right.
Okay? So there you go. All right. So implication is tricky, okay? It is a little bit more tricky than and or.
I should also probably mention I actually, as class started, just realized what we were doing with this homework. So
Oh,
yeah, it just couldn't connect with me. I was wondering how relations relate to less than or equal to, because because I thought literally relations were just a set
Mm-hmm.
that were a subset of the Cartesian product of X in itself.
Yep. Well, that's why I got office hours. Yep. Okay, so let's move on to transitive. Okay, is less than transitive. If A is less than B and B is less than C, does that imply A is less than C? Yep, it certainly is transitive. So now we ask, is it partially ordering? It is not, because it's not reflexive. And if it's not partially ordering, it cannot be totally ordering. So only these two apply to the relation less than. This one is greater than or equal to. Okay, I think this is not the quite last one, but close. Okay, so if we look at greater than or equal to, we apply the same reasoning. Okay, so we first start with reflexive. Is a integer value greater than or equal to itself? Is it guaranteed all the time? Yep. Okay. So it is reflexive. Is it symmetric? It is not symmetric. Okay. A is less than or equal to B does not always guarantee B is less than or equal to A. Sometimes, yeah, if A and B turn out to be the same thing, yes. But if A and B are two different things, no, it is not symmetric. So it is not symmetric. Is it anti-symmetric? If A is less than or equal to B and B is less than or equal to A, does that imply A and B are the same? Yep, go ahead. Greater than or equal to, yeah. So if A is greater than or equal to B and B is greater than or equal to A, does it imply that A equals B? The answer is yes. Okay? Now, okay, I'm just going to take a little detour here and ask, can we prove these things using Boolean algebra? Okay, so let's just focus on the anti-symmetric one and see whether we can use Boolean algebra combined with normal algebra to prove that. Okay, so anti-symmetric is basically saying, well, it's the same thing, except this time we have greater than or equal to, so I'm just going to change this to this. Okay, all right, so now the question is, how do we guarantee this part here? The quantifiers are not as important in this case. The for all part is not as important. Can we prove this using combining algebra with Boolean algebra? Okay, what you know about those two. Okay, how do we prove it? So this is how we can do it. So I'm just going to do this step by step. Okay, and it's going to be very tedious because I'm not using the equation stuff. Okay, so I'm just copying the original thing first. Okay, and we'll see where we can go with this. Okay, so this entire expression is the same thing as E is greater than, okay, so this time we need more stuff. Oops, that's not an and, that's an or. I'll spell this out and explain it once I'm done with this stuff here. Okay, so what did I just do? I broke up the greater than or equal to into greater than or equal to. And yes, that's exactly what I said. I broke up the greater than or equal to into greater than or equal to. Okay, so if you just listen to what I said and if you just look at the words, it doesn't make sense because I'm basically saying it is what it is. It is what it is, which doesn't make sense. Okay, but if you group the words in a different way, then it makes sense. Because I said that I broke up the greater than or equal to comparison into a greater than comparison or a equal to comparison. That was what I meant. Okay, is that okay? Okay, so at this point, what can I do about this? We can use distribution. So you can look at the or as if it is a addition. You can look at an AND as if it is multiplication. So FOIL also works in Boolean algebra. Is that okay? So what is FOIL? So what is FOIL in normal algebra? Okay, you got A plus B times D plus E, right? Okay, I'm missing C somewhere, but it's okay. Okay, it's not part of, it's not important. So now this thing is just, AD plus BD plus AE plus BE, right? That's FOIL. Are we good so far? Does anyone feel that urgent need to go back and take algebra again? No one? Okay. So I'm claiming that you can do the same thing in Boolean algebra. In other words, you look at an OR as if it is a plus in normal algebra. You look at an and look at it as if it's a multiplication in normal algebra. So you can FOIL the Boolean expression. So what happens when you do a FOIL on this one? Then you're basically saying, okay, E is greater than F and F is greater than E. That's one way to combine those two, right? Or, what is the other one? E is greater than F and F equals to E. Or E equals to F and F is greater than E, or E equals to F and F equals to E. Do you see how I just did a FOIL? It looks kind of tedious, which it is, but do you see the approach? Yep.
So you're saying that FOIL works no matter the construction of the, like we can follow basic algebra rules no matter the construction?
In this case, it works the other way around too, but I'm not going to talk about that yet, okay? So FOIL also works when you have AND inside and the OR outside in Boolean algebra. Not in normal algebra, okay? In normal algebra, that doesn't work, okay? But this is normal algebra, right? Yeah. So are we doing okay so far with this? Applying FOIL in Boolean algebra, okay? So then we look at this and go like, that doesn't look any simpler than before. That just looks super ugly. Well, but now you apply your normal algebra and you say E is greater than F and F is greater than E. That's not possible, right? That's just false. So I'm going to use a false here. Okay, we have another OR. This one says E is greater than F and yet F and E are the same. That has to be false. Okay, it's not possible. Look at this one here, kind of the same deal. Okay. And then you look at this one here and go like, I think that's a little bit redundant because all it's saying is E equals to F and F equals to E. So in normal algebra, you just go like, we just need to keep one of them, right? So you just keep one of them, like F equals to E. And then the whole thing implies F equals to E. So now, all the false would go away because this is a OR expression. So in an OR expression, 0 or false doesn't do a single thing. False is the identity of disjunction, okay? Because when you say or false, it doesn't do a single thing. It's just like plus 0, plus 0, plus 0 doesn't do a single thing. So all of this is now just going to collapse to F equals E implies F equals E. Okay. So when you look at this, what can we do about this? If one side is true, the other side is guaranteed true because they are the same thing, right? If one side is false, the other side is guaranteed false as well because they are the same thing. Is that okay? Because there are only two possibilities. Either F equals to E or they do not, right? But in either case, the implication is true. So this entire thing just boils down to true. Is that okay? Yep.
So is your general goal to try to make like the left side of an implication simplify to the right side?
Nope.
in a situation like
Nope.
this? Or
My objective is to get to here. So that's the overall objective, is to say that this expression is true regardless of how you choose your E and F. Yep.
So this would also show, say, if you had the instance where it wasn't guaranteed false, but it was true. It was the one that you did.
It can be true, but it can also be false, like that one.
No, there was one that it was we used anti-symmetric, but what was it? It was 3, I think.
Yeah.
Where it,
You can use you can probably use algebra for that one too. Yep. You can use Boolean algebra in that case. Because, well, you have to use normal algebra, because normal algebra will let you flip the size of the comparison, because A equals B and B equals A are the same thing. And that is not Boolean algebra, that is normal algebra. Is that okay? So are we good so far with, kind of the proof of this thing? Okay. All right. So we know it's antisymmetric, it is reflexive. We got one more. Is it transitive? If A is greater than or equal to B and B is greater than or equal to C, does it imply that A is greater than or equal to C? Okay, so it is transitive. Well, if it is all of those, then we know it is partially ordered. Okay, but now the question is it totally ordered? If I pick any two integers, can we claim that, okay, let me name the integers. Okay, if I pick integer A and integer B, can I claim that A is greater than or equal to B, or B is greater than or equal to A? Well, if that is defined, then it is also totally ordered. That's the one missing piece. That's the one thing between partially ordered versus totally ordered. So are we good with this question so far? Okay. And this is question number 6. I think it's the last one. If R, is it? There's one more? Oh, there's a little bit more. If R is a relation defined over X is known to be reflexive. Okay, so don't ask me why, but it is reflexive. Which one of the following do we know for sure, regardless of the actual definitions of R and X? Okay, so we know it is reflexive already, and I just want to know what else what is implied by that. Okay, all right. So we look at each one, okay, and then we'll look at none of the other answers can be confirmed last, okay, because obviously that one should not be first considered, because you have to look at all of the other ones first. So we look at the first one. The first one says the cardinality of R is guaranteed to be different from the cardinality of X. Nope, you cannot guarantee that. If you just look at greater than or equal to, which is reflexive, R is quite a bit bigger, but then you can look at equal to, in which case R and X have the same cardinality. Does that make sense? Did everyone understand what I just said? The equal to relation, in the equal to relation, the cardinality of the relation is the same as the cardinality of the set itself. So we good? Okay. So this cannot be the answer. Let's look at this one. They're guaranteed to be the same. That's not true, because if you look at R as greater than or equal to, then the relation is quite a bit bigger compared to the set that the relation is defined over. Okay. You look at the next one. R is greater than or equal to X in terms of cardinality. That's our answer. Okay. But just to make sure, okay, if I'm answering a multiple choice question, I always go through all the possible answers to make sure that what I suspect is right is actually right by confirming everything else is false. Okay, so we look at this one here. It says the cardinality of R is less than the cardinality of X. Any relation that meets this requirement cannot possibly be reflexive. Okay, it can be some other things, but it cannot be reflexive. So now we just kind of confirm that this is the answer. Does that make sense? Because if a relation is reflexive, it means every element in X relates to itself. So that guarantees us the cardinality of X many relations in R. Now, can it have more? Sure, it can have more, just not less. Okay. Question number 7. If R is a relation defined over X and R is known to be symmetric, so this time it is just a different property, which of the following do we know for sure regardless of how R and X are defined? So same kind of question. I'm looking at the cardinality and say, well, do we have any idea of how they should relate? The first one looks kind of good, right? Because if it is symmetric, then the cardinality of R is twice the cardinality of X. That is actually not true. Look at an empty relation. Okay, look at X only having 3 elements, A, B, and C. Okay, X only has A, B, and C, and R is an empty set. Is it symmetric? It is symmetric. Does 0 equal to 2 times 3? No. So this is not the answer. Moving on to the next one. R does not equal to X, or the cardinality of R does not equal to the cardinality of X. That's never guaranteed. Okay, so we cannot pick that one either. The cardinality of R is greater than or equal to the cardinality of X. I just use an example that illustrates that it's not guaranteed. So we have to rule that one out too. The cardinality of R is odd. Okay. No. The cardinality of R equals to the cardinality of X? No. The cardinality of R is guaranteed to be less than the cardinality of X? Nope. So what you need to do is to come up with a counterexample in each case and say, okay, this is an example where we have a set X and then we have this relation, and by definition it is symmetric, but it does not meet this requirement. So this requires you to think kind of in that direction of coming up with counterexamples. Yes?
One thing that I was struggling when I did this was, based on the way you say it, you're not implying that it's only symmetric. It could also be reflexive.
That is correct. So now we have this one here. Okay, R is even, or the cardinality of R is even. That is not guaranteed. So the only sensible answer is none of the other choices can be confirmed. Now, what if I say that it is only symmetric and nothing else? That gets a little bit tricky.
Still can't.
Huh?
I still don't think you can.
It would still be none of the above because the cardinality of R has to be even in that case.
No, it doesn't have to be even.
It has to be even. Okay, tell me why it doesn't have to be even. Yeah, go ahead. Now remember, it is only symmetric and none of the other properties.
Yeah, you're saying it has to be even?
It has to be even.
I'm saying it wouldn't have to be even.
Okay, give me a counterexample.
The equal to relation over a set of 1 elements. And let's say that the element is...
Then it is not just symmetric because it is also reflexive.
Okay, it could be 3 elements then.
Okay, so if it's 3 elements, but if as long as the relation is equal to, it is always reflexive. You have to pick something that is not reflexive.
I was thinking of it as like, because they're the same tuple. You know, so there's not necessarily 2 of them. But I guess, yeah, you're right.
Yeah.
Equal to gives one.
Once you, if I put the extra constraint of it is only symmetric, it is not reflexive, it is not anti-symmetric, and it is not transitive, okay, then it has to be an even number.
Wait, it's still, if it was reflexive, and let's say
Uh-huh.
there's 3 elements, then we know for sure there's 3 tuples, right?
Okay.
Okay, and if it is symmetric,
Mm-hmm.
it could be those same 3 tuples.
I-
You're saying that if one's in there,
Mhm.
one's in there, 2's in there, 2's in there, 3's threes, you add three threes, and there's still only three elements. So that's an odd number.
Hmm.
And that fits that.
Okay.
Yeah. Because there doesn't add extra to
Right.
it.
It doesn't have to be all of them. So you're right. Okay. So you can define something that is only symmetric but not everything else. That is, so nothing can be said about it.
Yes.
Yep.
Yeah.
Yep. So you're right. Does everybody catch that one? Yeah, because Nick thought of an example, that I did not think about, because, okay, I'll give you an example. So we got A, B, and C in one set. This is X, and we want to define a relation so that it is only symmetric, nothing else, and has an odd number of elements. Okay, so the way we do it is to say R equals to just AA.
I'm actually saying that the equal to one works in this case because if
The
you have
equal to?
then you have AA, B, C, C.
Yeah.
And if you say AA is in there, AA is still in there. There's only three things. So
Yeah, but it's reflexive already.
which would still give you an odd number.
No. But remember, the premise
Oh,
of the
only
question is
symmetric.
it cannot be. It is only symmetric. It cannot be reflexive, nor transitive,
Okay.
nor anti-symmetric.
Okay, then you're
Yeah.
fixing my example.
Yep. But that's the line of thinking, is to come up with examples and go like, how can I come up with an example to show this, right? Yep. All right. So I'm gonna turn in my quiz, and if I get less than a perfect score, something is not right. So I got what, 7 points out of 7, I think. Okay, cool. All right. So how did you guys like this homework? It's tricky, okay?
It made you really have to think about everything.
And study, yes.
Yeah.
But that's good, because that means the homework is doing what it is supposed to do. Because you have to.
The ones I got wrong, that's for sure. I missed one on the, I think it was the first one. I didn't put
Okay.
anti-symmetric. I'm like, no. Why?
Just out of curiosity, if you could show us what was the average score on this one?
I do not know. I cannot show just the aggregate, without showing, the individual. Not right now. So
I'd be curious about that too.
Yeah.
I can turn on, ranking in the grade book,
Oh,
so you guys can see how you rank in class.
oh yeah.
You prefer not to.
I mean, how many students are in this class, first of all?
There are about 50, close to 50.
So if
Yep.
you're like
That'd be nice.
50, that's pretty bad.
Yeah, but well, okay.
Everyone's like
Well,
super
doesn't
high
it-
though.
But I don't grade by curve, okay? I do not assign letter grades by curve like some well-known four-year universities. So I'm not going to say only the top 2.5% can get the letter grade of A. So
Everyone can have an A.
technically everybody can have an A as long as they meet the 87.5% requirement.
Does that mean like we could have only like 5 spots where people like there's several people who are number 1 in the class, and then, like everyone else is like
Not in this class, not when I'm grading. I never use curve for grading purposes, unless too many people, or unless there's no one getting A's because of the test being too hard. Then I'll pull the curve, in order to kind of make it correct.
I'd be curious to see 310s.
310.
Like for my class, I kinda saw that.
310 usually has, I would say, about at least 1/6 of the class usually getting A's.
What about the second exam? I want to see that one specifically.
I can go back and collect that statistics, but not, but
That one was a difficult exam. I remember
yeah,
it being real rough.
yeah, possibly. All right, so we are now getting back to propositional logic. Okay, so it's still here. And we just talked about the completeness of CNF, okay? So the completeness of CNF, basically says, if you give me any Boolean expression, I can always turn it into a CNF, conjunctive normal form. So I'm not going to spend the time to redefine what is conjunctive normal form, because that's what we did on Monday. Okay, so I'm not going to spend the time to redefine that. Okay, so now what we want to do is to go like, okay, so what have we gotten at this point? Okay, the first thing is it doesn't matter what expressions you want to express normally, in a human readable way. I can always convert that into a CNF, a conjunctive normal form. Okay, is everybody buying that after looking at this particular example? Okay. Okay, so that's really important because that means if in Boolean algebra, there's actually no need to define, implication, if and only if, and stuff like that, because CNF covers everything. You can just convert everything to CNF, conjunctive normal form. Now, if you are thinking a little bit outside of the box and just go like, well, if there's CNF, which is conjunctive normal form, what about disjunctive normal form D and F? There is such a thing as well. Okay, so and the answer is anything that you can express as a Boolean expression can also be expressed as a DNF. So CNF, DNF, and the general Boolean expressions, they're all equally expressive. If you can express it in one, you can always express it in the other two. Okay, it's just a matter of, well, can you read it and understand what it means? Okay, as a human. That's the only difference. So are we good so far with that? Yes? Hopefully? Okay. So what does that mean? Well, that means, anything that you want to put into the iota that involves implication, kind of nasty nesting of, the operators and whatnot, we can convert all of those into CNF. Are we good so far? Then you go like, but according to the definition of the new definition of well-formed formulae, we are not supposed to have conjunction in the expressions. Do you guys remember that? Because we only have disjunctive terms inside as well WFF, the well-formed formulae. So what are we going to do? Easy. Break this up into two different items in iota. So let's just say that originally, I had this as one single item in iota, and I claim that this expression is always known to be true. Okay, because things in iota are given, they're always true. Then we switch to the new system of using CNF, and then suddenly go like, oh, we cannot have implications. We cannot have negation operating outside of just a variable, and we certainly cannot have an AND expression inside as a component of an OR. Those are all not allowed anymore. Okay, but because we know that we can translate everything, all the Boolean expression can eventually translate into a CNF like this. So now what I put into iota is just going to be, this item on its own is one item in iota, one element in iota, and then this element on its own is another element in iota. I just have to break it up into two different elements in iota, and then it really still has the same meaning as before. Is that okay? Is that making any sense? Are we good so far? Yes? Okay. So the first implication, I'm just going to summarize, is everything that we could express using the old traditional human readable propositional logic system, we can still express all of that stuff here. Okay, it just looks kind of awkward, and long expressions got broken up into smaller expressions, but we can still express the same thing. Is that okay? There's a second implication. Do you guys remember what I talked about before CNF? Starts with the R, but it's not relation. Resolution, very good. So what does this have anything to do with resolution? Let's go back and look at resolution again. Okay, so we scroll up just a little bit to look at resolution again. And this is the resolution transformation rule. What does it look like to you? We're looking for disjunctive terms, right? We're looking for disjunctive expressions, and we're looking for two that has a particular pattern. Okay, Whatever phi or rho is, I don't really care. For all I know, those can be blah 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 or blah 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 or blah 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 or blah 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 all day long. Okay, doesn't matter to me. All I want is one has psi, and the other one has the negation of psi. Okay, but do you see how CNF fits into this picture? Nope. Okay, so let's check out what a CNF looks like. Okay, so we look at. So remember, when we see a set of two expressions like this, we are basically saying this expression is true and this expression is true. There's an implicit conjunction here. And then we go back and look at what a CNF looks like, through all the derivation like that. Okay, forget about this and, okay, because we can now replace this and with a comma when it is considered elements in a set. Do we see the connection? When everything is expressed in CNF, we can easily apply resolution. We can easily look for the pattern and apply resolution. Is that okay? So CNF allows us to use resolution over and over and over again. Are we good so far? What about the result of resolution? When we throw that back into the pool of well-formed formulae that are known to be true, does it fit the format of everything else that are already known to be true? Okay, let's check it out. Okay, so let's go back and say, if we do apply resolution, the result of resolution, does it have the format that lends itself to further resolutions? What do you think? It's a disjunctive term, right? So this can now be used in the next step into something like this. We just have to find another expression that it can resolve with, if possible. Is that okay? Are those things connecting or not? Some people are nodding. Some people are abstaining. Yes, go ahead.
Can you say that one more time?
Okay, yes, I can say it one more time. So this time we are focusing on the result of resolution, and we are asking, does the result of resolution, is it in a format that lends itself to be used in further resolutions? And the answer is yes, because it is also just a disjunctive term. It's a simpler, well, not necessarily simpler, but it's a disjunctive term. It's kind of like concatenation, right? So we are taking the first term here, we're taking the second term here, we get rid of the part where one side is not negated, the other side is negated, and then we concatenate the other two. So the end result is going to be something that is also well-formed, guaranteed. Is that okay? We're good? All right. So now we got two things, okay? That's good, okay? Because the first thing that is good about all this is, what is the space of well-formed formulae? Okay, I'll give you an example. Okay, so I'll give you an example of only two variables at this point. Okay, so we switch to here, and we say alpha has the usual, 0, 1, and then just p and q. Okay, so we only got two variables. So of two variables, how many well-formed formulae can we come up with using the CNF, using the new definition of well-formed formulae? Okay, so let me ask you, is this well-formed? Can we look at this as a disjunctive term with only, disjunctive expression with only one term? Yeah, it's okay. What about this one? Okay. Okay, what about, I'm going to use plus, instead of the bar as or. Okay, so that's another way to express or. What about this one? Is it well-formed? Okay. What about this one? Well-formed. Okay. What about this one? Well-formed. That's well-formed. Okay. well-formed, 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 well-formed. Are we good so far? Okay. So now the question is, if I ignore the ones, the true and the false, okay, because those are kind of like, they're not very interesting. If I ignore those two and only focus on the ones that involve at least one variable, how many are there? In this case, we have 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them. Okay? So let me ask you this question. And that's only for 2 variables. If I have 3 variables, P, Q, R, okay, how many disjunctive expressions can I come up with that are well-formed, ignoring the constants? If I have 3 of those, how do you think about this problem? How do you count the number of disjunctive expressions that can involve, the non-negative version of a variable or the negative version of a variable, or missing and say that it's not used in here?
Count them as like permutations.
Not quite. It's actually easier than permutations. Permutations, basically says without replacement, but in this case, it's actually easier. Okay, so let me show you a way to do that. Okay, so we have P, Q, and R. Okay, so we can say, when P is here. Okay, so we say, let me think of a terminology to say that it's here. Okay, so plus means it is P itself is in the expression. Okay, so there's that, and there's that. Those are all the single variable expressions. Are we good? Oh, wait, but we also have the negations. Oops. Right? Then we say, okay, we can have this, we can have this, we can have this, or the negation of that. We can have this, or the negation of that. Okay, so I forgot about the plus over here. And then we can have the plus or the negation of the last one. Do you see what I'm trying to do here? Okay, so now we can have the second one. So what is a systematic way to look at this? For every single variable, it can be missing, it can be non-negated, or it can be negated in an expression. Does that make sense to you? Okay, so each one has kind of 3 choices. Okay, so P has 3 choices, Q has 3 choices, R has 3 choices as well. So just based on that discussion, how many different expressions can I have? Huh? So how does 3 relate to the other 3? In other words, we got 3 variables, and for each one there are 3 possible choices, right? So how do we relate those 2 3s? Okay, I can think of 3 possible answers. 3 plus 3, we only got 6. Quite obviously, we have more than 6. Okay, 3 times 3, which is 9. Okay, I think we got more than that because I think we still haven't really played with Q yet. Okay, what about 3 to the power of 3? The first 3 has to do with there are 3 choices for each variable. The power itself has to do with the number of variables. Okay, so if you answer that question, as 3 to the power of number of variables, I'll give you almost full points because we have to subtract 1, which is all 3 variables are missing. Now, if all 3 variables are missing, we're basically talking about false. Okay? Yep.
Is it always the number of variables to the power of 3?
It's 3 to the power of number of variables. Okay, so so an analogy to think about this is
see it.
yeah,
I see it.
yeah.
For
Okay,
each
so you
one,
got
there's
it.
3 possibilities.
Yep.
Okay.
But the biggest question is that number finite? Okay, if I say we only got n, which is a fixed integer of variables, okay, the number of possible expressions is that number finite? Is it just like, oh, okay, it looks like a big number, but it is a number, it is not infinity? Is that true? Okay? But doesn't that mean that your entire space of well-formed formulae is finite? There are only so many well-formed formula expressions in this entire space. Yes? I think we just found a fix of one of our problems, being the space is infinitely large. Is that okay? Does everybody understand why we just solved one of the key issues of propositional logic in a more traditional way?
We're no longer searching like this giant, unsizable haystack.
Exactly. We no longer have an infinitely large haystack. Now, the haystack is still large because it is still 3 to the power of number of variables. So if you have 16 variables, we'll be looking at 3 to the power of 16, which is it's still a pretty big number, okay? But it's finite, okay? The key is it is finite. We don't have a problem of we don't know when to stop anymore. We know that, okay, it's just going to take a while to figure out the answer, which is much better than saying, I don't know when we're going to stop. Is that okay? So we got most of the key pieces in place, okay? The one missing piece is, how do we use this to prove theorems? Okay? That is the one remaining piece that makes it kind of like, yeah, but how do we make use of this? Okay, we got resolution and we keep resolving and resolving and resolving, but how do we get to the theorem that we want to prove? Okay, so that remains as a question. So there are several ways to do it. You can exhaust the entire space. Okay, you keep resolving until you can no longer resolve, and then you look at the theorem itself, which is going to be another Boolean expression, break it up into a CNF and see if all the components are in place. Okay, that's one way to do it. But there's another way to do it. Okay, it's called proof by contradiction. So this is when we are kind of switching gear yet another time, okay, within this module to talk about a concept that is kind of disconnected with the other ones, but eventually it will connect with all the other ones. So we're going to talk about proof by contradiction. How many people have some exposure to the concept of proof by contradiction? Okay, we got a few people, but most people may not have a whole lot of exposure. So where did you guys learn about proof by contradiction? Which math class? Calc 1, okay. But since the prerequisite of this class is only pre-calc, I cannot assume people have exposure to those classes.
Maybe trigonometry.
Trigonometry?
Possibly.
Okay. So but it doesn't hurt to look at it again. Okay, so we're going to look at proof by contradiction again, but this time we look at it from the logic perspective. Okay, so proof by contradiction, so this is my own proof of proof by contradiction itself, because I have to know that the mechanism of proof by contradiction makes sense. Okay, so this is how I prove the technique of proof by contradiction. So we will start with what we call a corollary. Okay, so a corollary is kind of like a mini theorem. Okay, so you can just look at it as a theorem that is not really that helpful by itself, but it is kind of important, to prove a more important theorem. So we're going to prove this little theorem first. Okay, so this little theorem starts with this expression. Okay, this is the original expression, and we want to see what we can do about it. But the first thing we also want to do is to look at this and go like, okay, does it make sense to you? P implies Q implies P and R for some R implies Q and R for the same R. Does that make sense? Okay. To some people, it makes sense intuitively. It's like, yep, that makes sense. Okay. To some other people, go like, no, I'm not really sure about this. Okay. So if it makes sense to you intuitively, you still want to go through a rigorous proof by Boolean algebra just so that you go like, okay, now we know for sure it's not just my intuition telling me that it is true. It is actually now proven by rigorous steps that it is true. Okay? So now we go through all the steps. What did I do from line 1 to line 2? Yep.
Real quick, can you
Yeah.
say the top part one more time? What
The top part.
Just the base corollary. What it's saying there again?
That's exactly what you see is what you get, really. It says P implies Q, implies P and R implies Q and R.
Do you have a layman's terms for that, maybe?
That's it.
Exactly is R though.
R can be anything. All it says is if you know that P implies R is true, okay? So because if it's false, then the whole implication is going to be true anyway. So that's not very interesting. So it is only interesting when P implies Q is true to begin with, okay? So if we know that P implies Q is true, then we also know this is going to be true. What again? What is guaranteed true if P implies Q is already known to be true? Pick some R value, okay? R can be a huge expression, can be just a little expression, can be anything, okay? All I claim is P and R is now going to, for sure, imply Q and R. In other words, you can introduce an extra term in the implication on both sides.
Because it'll be true.
And I claim that this implication is guaranteed true if that implication is true to begin with. Okay?
And I don't want to get too deep on it, but how does that relate to contradiction?
Oh, because I'm going to use this later. So we'll see it. Okay? So the first thing is to go over this proof here, which may not be the simplest one, but nonetheless, it gets the job done. Okay? So from the first line to the second line, it is I'm just applying the definition of implication. So that P implies Q, now it is becoming not P or Q. That's just the definition of P implies Q. Okay? And then I apply it to the other side as well. Is that okay? And then in the next step, I apply the definition of implication again, but this time I apply it to this particular implication. So I negate this entire side or this entire side over here. Is that okay? Okay? All right. So going from here to here, I apply De Morgan's law. So the negation of an or becomes the negation of whatever is inside and the negation of whatever is inside. Then double negation is canceled out, so we just get P itself. Is that okay? All right. What about the other side? Well, the other side is a lot simpler because all I did was to dissolve the extra parentheses that is not needed because of the associative law of algebra. Is that okay? Because the
I'm kind of stuck on the second line. Where did this not come from?
I mean this not here.
No, the second. No, all right. I'm considering the base case P implies Q as the first line.
Okay. So you're thinking about where this is coming from?
Yeah.
The definition of implication?
Oh, okay. All right, I just forgot.
Okay. All right. So where were we? Oh, we're here. So now we have to go from here to here, okay? So to go from the fourth line to the fifth line, I'm just dissolving the unnecessary parentheses, this one here, and I just break it up into smaller terms. Are we good so far? Okay. And then from here to here, I introduce the identity of conjunction. So this one is just simply not P, and I have to make it look more complicated and say, hey, not P is really the same thing as not P and true. Now, you might question the motive of doing that, but it is not wrong. Okay? And I do the same thing with not R. So when it was just not R by itself, now it is not R and true. Are we good so far? Okay? So from this line, okay, this one is now becoming Q or not Q. This one is also becoming Q or not Q. Now, once again, you might question the motive. It's like, why did you do that? I mean, but you cannot say it is wrong. Because Q or not Q is guaranteed true. Because if Q is false, not Q is going to be true. If Q is true, not Q is going to be false. One of them has to be true. So the disjunction has to be true as well. Are we good so far? Okay. Then from here to here, I just use FOIL. Okay, I just expand it out, so I can say not P and Q becomes its own little term. Not P and not Q becomes its own little term over here, and these two terms are ORed together. It's basically a miniature version of FOIL. I mean, it's just distribution here. And I do the distribution on the other side from here to here, so that not R and Q becomes its own little conjunctive term. Not R and not Q becomes its own little disjunctive term over there. Okay? So I make everything more complex, and then I make it simpler, with this step over here. This one is just rearranging. Okay, you can see how I just kind of rearrange things a little bit. I moved this one over here. I moved this one over here. I moved this one over here and reordered Q and R because I like everything to be in alphabetical order. And I moved this one over here. So it's just a whole bunch of reordering. So when we are reordering in expressions, which axiom did I use? It starts with a C, commutative, right? So, and then from here to here, I did some simplification. Some terms were lost, okay? And some terms got simplified. So can someone tell me what terms got lost in this case? Or what got changed? From the third line from the bottom to the second line from the bottom, what got changed? Let's look at something that is still here, okay? Not Q and not R, yeah, that thing is still here. And then not P and Q is still here. But Q and not R and Q and R are now gone. I skipped one step. What step did I skip in the proof? Factoring. Okay, I skipped the step of factoring because it would, if I were to introduce another step, okay, to kind of fully explain what's going on, it would be Q and then open paren, not R or R, close paren. Okay, because it's just factoring. We got Q and Q here, so they can now be factored into the same conjunction term by combining the not R and the R using an OR, and that's inside the conjunction. Is that okay? So that's how I simplified not R and or R out of, and it becomes just one. And then over here, I do the same trick with P, not P. I do another factoring because they are both ending with not Q, but then one has P, the other one has not P, and then these two expressions are connected by an OR, so I just did another factoring. So now we have one and not Q, which is just not Q, or not P and Q, or Q and true, which is just Q itself, and blah, blah, blah. So how did that become just one? Once again, actually this time I didn't quite skip a few steps, maybe one. We got not Q here, or Q. Not Q or Q is true, so that's whole true. Okay, so now that we know this expression is always true, what does that mean? What is the meaning of all of these steps? All it means is this implication is always true. That's all. That's the conclusion. Yep.
How did you get rid of the not P and Q and then not Q and R?
Not, how did I get rid of?
So I see how you got rid of the one and not Q and the Q and one, but the other two terms.
It doesn't matter because once you have one true in a disjunction, the whole thing is going to be true.
Yeah.
Yep. So this implication is always true. That is our corollary, is to basically say, if you know P implies Q is true, then no matter what R is, okay, you can always add that in a conjunction with P and Q, and then P and R would also imply Q and R. That's all it is saying. Yep.
Just to clarify on like the last part,
Yep. Yep. If you have a big OR and one of the components of the OR is true, then the whole thing is going to be true. Yep. Okay, so this is the corollary. And how I use this corollary is to look at the following. So this time I just say that, okay, let's go back to theorem proving first. Okay, what is theorem proving? Theorem proving means that you're given certain things that are known to be true to begin with. Okay, the theorem itself, which is another Boolean expression, has to be somehow implied by things that are known to be true. That is proving a theorem. And it doesn't matter which branch of math you're talking about. You can be talking about linear algebra, you can be talking about calculus, you can be talking about differential equations. That is universal to all proofs in a logic sense. Okay? So in this case, what psi is representing is psi is basically just saying everything in iota. Okay? String all of those things together with an and. Well, but that's already implicitly ANDed together. I'm just making it so that it is one gigantic AND expression. Is that okay? So that's what psi is. Psi is basically saying, give me everything that is known to be true. Okay? And we know that everything that is known to be true in a propositional logic system are contained in iota, the set. Is that okay? So that's what psi is. Phi, on the other hand, is the theorem that you want to prove. Phi is the one expression that your professor says, okay, go ahead and prove that phi is, in fact, implied by everything that is known to be true, which is basically the conjunction of everything in iota. Okay? So if phi, in fact, is a theorem, then we will have psi implies phi being true. Does that make sense? Okay? But that's only if phi is, in fact, a theorem. Is that good so far? Okay? So if you ignore the rest and just look at this one here, this is the essence of proving a theorem. You start with everything that is given to you and known to be true, and you have to somehow follow a chain of derivation or whatever and say that it implies phi, which is the theorem that you want to prove. Okay? So now we look at this and go like, oh, that looks like an implication to me. And from our corollary, we just learned a trick and say, if you tell me an implication is true, now I can do something wonky to it and just say, hey, this thing and something is implying that thing and the same thing. As long as I'm using conjunction and what I'm introducing into each side of the implication is the same, then the implications should still be true. Is that making any sense? So from line 1 to line 2, that is how I applied the corollary. Is that okay? Does everybody see how I just made use of the mini theorem that I proved earlier? Yes? Basically, look at this as R. Look at this as P. Look at this as Q. Now you start to see, oh, okay, it's the same thing that we proved earlier. Yep.
And you were able to choose it as not.
I can choose anything. R can be anything. Yeah. Yes. The whole point of the mini theorem is it doesn't matter what R is. R can be a constant of true, no problem. R can be a constant of false, no problem. R can be anything, and this implication will still hold true. So I know we are running out of time, but this is important. This is really important. Because, oh, but hold on a second here. What is phi and not phi? It's a contradiction. It is guaranteed false. Okay? But that means if I start with everything that is known to be true and put it into the same conjunction as the negated theorem, the theorem that I'm supposed to prove, that conjunction somehow has to arrive to a conclusion of, nope, this is not possible. It is false. Right? That is proof by contradiction. Okay? So if I were to use the next 10 seconds to summarize what is proof by contradiction, this is it. Start with everything that is known to be true. Combine that with the negated theorem. the conclusion of that should be false. Okay? So now we have all the major pieces. Okay? Over the weekend, read the module so that we know how all of these pieces are connected. CNF, resolution, proof by contradiction.
So in this case, psi is not a theorem.
In this case, psi is not the theorem. Psi is everything that is given to you as, okay, take out all of these, they are known to be true.
Yeah.
We want to
Or
connect,
psi, the circle with the line.
that's phi.
Phi, whatever.
So phi is the theorem that I want you to prove.
And it's not a theorem in this case. Oh,
No, it is. If you can arrive to this contradiction, that means phi is in fact a theorem.
I'm gonna need to think
How
on
did you end up getting?
Huh?
How did you end up getting psi and?
I just introduced this because of the theorem. The mini theorem that I introduced earlier says that I can introduce, as long as this part is the same on both sides, the implication would still hold true. So I just choose to use something that is wacky, that will guarantee this side is going to be false. Yep.
Oh, if your theorem works, then you get everything. If your theorem works, then you would get a 1, right?
Yeah, let me turn off the